Greetings, my name is Mike Levis and I'm an instructor with the Mount Hood Ski Patrol Avalanche program. Today's topic is weather. Weather is considered the architect of the avalanche. Weather, both current as well as past weather history, will determine the structure of the snowpack and ultimately the potential for an avalanche. Let's get into it. Let's start by reviewing our old friend, the Avy Triangle. The Avy Triangle is a great tool to visualize the key factors that determine the likelihood of an avalanche: weather, snowpack, and terrain. In this discussion, we're going to focus on weather, which, as we previously mentioned, is considered the architect of the avalanche. Other modules will focus on snowpack stability and terrain in some detail. Our goal today is not to make you meteorologists or weather forecasters, but rather to give you the tools and understanding to assess if the weather is increasing or decreasing the avalanche risk. In particular, understanding the critical threshold values where wind and precipitation significantly increase avalanche risk is important. Also, it's important to be able to assess trends in temperature and precipitation and the impact these trends have on snowpack stability. Most avalanche forecasting sites, such as NWAC, have views of weather history, both temperature and precipitation, for the forecast region. By looking at the past weather history, you should be able to get some perspective on what is happening in the snowpack and whether the snowpack is getting more or less stable. When we think about weather and the effect it can have on avalanche risk, we think about precipitation, wind, and temperature. Precipitation creates the snowpack. The type of precipitation, rain versus snow for example, can have a great effect on stability. The duration, how long the precipitation occurs, and the intensity, how many inches of snow or rain per hour are being deposited, can have a huge impact on stability. For example, which do you think will be more stable? 2 feet of snow deposited over 2 weeks, or 2 feet of snow deposited over 24 hours? Wind can change snowpack stability with or without precipitation. Wind can move snow, increasing snow depth and loading in one area and reducing it in another. Temperature, and more precisely temperature trends, will affect the bonding in the snowpack, and this will affect snowpack stability. Temperature gradient within the snowpack will affect the nature of the snow crystal formation, which will affect bonding in the snowpack as well. Western North America is broken down into 3 major climate zones based on the characteristics of weather, terrain, and snowpack. The Maritime Zone is along the west coast and is greatly impacted by weather fronts coming in from the Pacific Ocean. This is the zone we are in, and the zone we'll focus on for much of the balance of the discussion. The Continental Zone is along the Rocky Mountain Range and is impacted by cold fronts coming down from the pole. This zone is far inland and sees very little impact from the Pacific Ocean. The Intermountain Zone is the transition between the Maritime Zone and the Continental Zone, and it shares characteristics of both. Let's start by talking about the Maritime Zone. The Maritime Zone we are in has weather patterns determined primarily by winds coming in from the Pacific Ocean. This zone is characterized by heavy snowfall and relatively mild temperatures. Snow has a high moisture content and is very heavy. Avalanches tend to occur due to heavy loading from snow or rain and usually occur immediately after storms. Failures tend to occur near the surface, and persistent buried weak layers are rare. Weather observations are the primary tool for avalanche prediction. The Intermountain Zone is significantly impacted by weather patterns from the Pacific Ocean, but its temperature tends to be colder. This results in snowpack with lower water content, but still characterized by surface avalanching after storms. Because of the lower temperatures, rain is rare in midwinter, and therefore rain loading is not as much of a factor. In the Maritime Zone, like the Maritime Zone, forecasting is done primarily through weather observations. The Continental Zone is a considerable distance inland and therefore has little influence from the weather patterns from the Pacific Ocean. Cold weather from the poles has a much greater impact. This zone is characterized by much lighter snow with lower water content. Snowfall tends to be much less than in the Maritime Zone. The snowpack tends to be unstable for long periods of time due to persistent buried layers. It is not uncommon for an avalanche to occur due to a failure of a buried weak layer that was created months earlier. Avalanche forecasting in this zone relies heavily on observations of buried structures. Given the difference in the snowpack characteristics in the different zones, it's worthwhile to know the critical rate of loading that would load the snowpack to the point of failure. As the slide indicates, for the Maritime region, a snowfall of 1 inch per hour or more should be considered a danger sign for avalanching due to rapid loading of the snowpack. But what does 1 inch per hour mean? Is this new snow? What about wind transport? Wind transport could result in 1 inch per hour on the lee side of a slope in a snowstorm that's only depositing a ½ inch per hour. So when we talk about snow deposition rates, we're talking about the total deposition rate, both from the storm and from wind loading. And again, for the Maritime region that we're in, the critical rate is 1 inch per hour. So snowfall rate greater than 1 inch per hour is a red flag due to rapid loading of the snowpack. What other considerations should we think about? Increased snowfall increases stresses on pre-existing weak layers. Depending on the temperature profile, new snowfall may also contribute to the creation of new weak layers. Temperature profile will also affect the bonding of the new snow to existing snow surface. Cold temperatures will result in much slower bonding, for example. It's important to translate the new snowfall amount into water equivalent inches to get an accurate sense of the loading of the snowpack. 6 inches of new snow in Utah has a much heavier and lower water content than 6 inches of new snow in Mount Hood. Which do you think is heavier? Here in the Maritime zone on Mount Hood, we typically look at 10 inches of snow equals 1 inch of water. So some sort of ratio like that. The snowpack does not like rapid loading. Rapid loading greatly increases stresses on weak layers without sufficient time for the new snow to bond to the previous snow surface. Long multi-day events or creep events where small amounts of snow are deposited over an extended period, for example 2 inches per day for 2 weeks, can also load the snowpack, but the slower deposition rates allow new snow to bond to previous snow layers and reduce the likelihood of a slide. So lots of snow suddenly causes a much higher potential for an avalanche to occur. Rain on the snowpack does nothing to improve the stability of the snowpack. Rain on snow adds weight without adding strength. Rain weakens the bonds between the grains, which can result in wet slide avalanches. Rain also creates a slippery bed surface when it freezes and forms an ice layer. Rain can percolate down to the into the snowpack and lubricate a bed surface, facilitating a slide. The combination of warming, extra weight, and weakening of the snow bonds can initiate the rapid onset of an avalanche. Wind is the wild card that can completely change snowpack and loading. Wind-deposited snow can very quickly increase the loading on lee slopes even without additional snowfall, even in clear weather. Wind in the mountains is steered by the terrain, and loading patterns can change based on wind velocity and direction. Light wind is not strong enough to transport snow. Wind that is greater than 60 miles an hour will scour the mountain without redepositing the snow. Wind between 20 and 60 miles an hour will redeposit snow locally and should be a warning to check for wind-loaded aspects. More than anything, wind can affect the type, location, and timing of avalanches. So what do we need to think about when considering wind effects? First, think about the wind direction. Snow will be deposited downwind, so knowing the wind's direction will help determine what aspect of the mountain will be affected. Wind speed is another consideration, as we just discussed. As we mentioned on the previous slide, winds less than 20 miles an hour will transport very little snow. Winds greater than 60 miles an hour will transport the snow long distances, so lee slopes will not be affected as well. It's only for wind speeds between 20 and 60 miles per hour that snow transport should be a factor in loading. Wind duration will determine how much snow is transported. Winds that are sustained over hours or days will move much more snow than winds that are intermittent. So we've discussed precipitation and wind. Let's move on to temperature. Let's consider 3 separate topics: temperature during storms with precipitation, temperatures before and after storms without precipitation, and the effect of solar radiation on snowpack stability. Temperature will affect snow density. So if we look at temperature during storms, colder temperatures will create lighter density snow, while warmer temperatures, 20 to 32 degrees Fahrenheit, will create denser, heavier snow that increases loading. Very cold temperatures, below 10 degrees Fahrenheit, will change the crystal structure of the snow and will take a very long time to stabilize. So 20 to 32 degrees will create denser, heavier snow that increases loading. Colder temperatures, lighter snow, but takes a much longer time to stabilize. When storms are present, temperatures of both the air and the old snow surface has a big impact on bonding of the new snow to the surface of the old snow. Warmer temperatures improve the bonding between the newly deposited snow and the old snow surface. Temperature mismatches between the air and the old snow surface reduce the bond strength of the new snow to the old surface. Note that temperatures often fluctuate as a storm front moves through. Let's look at what happens when the temperature changes during a storm. Let's first consider what is referred to as a right side up storm. This is a storm that starts out warmer and gets progressively colder. Initially, with the warm temperature, the snow is denser and bonds well to the old snow surface. As the temperature drops, the snow will become lighter and less dense and will load the slope at progressively slower rates. So we end up with a light, fluffy snow over a wet, heavy snow. This offers less chance for a buried weak layer and should result in a relatively stable snowpack. Conversely, if we look at what's called an upside down storm, a storm that starts out cold and then gets warm, in this scenario we end up with wet, heavy snow over light, fluffy snow. This increases the chance for a weak buried layer and increases the likelihood of an avalanche that triggers naturally. On the next slide, we see NWAC weather data that gives an example of this. As you can see, temperatures start out cold and then get warmer. Corresponding snowfall shown in the lower chart will have an upside down pattern. So if you're looking at NWAC to look at weather history and you see this kind of pattern, you know that you are basically going to see wet, heavy snow on top of light snow. You could have buried weak layers, and you have the conditions that are more conducive to avalanching. So we've talked about temperature profiles during a storm, but what about temperatures before and after a storm? How can these affect snowpack stability? First of all, recognize that the rate of change of the snow structure is a function of temperature. Warmer temperatures near freezing will result in more rapid bonding of snow grains and a snowpack that stabilizes more quickly. Conversely, colder temperatures will reduce the rate of bonding between snow grains and result in a snowpack that stabilizes very slowly. Because of this, sustained cold will have a destabilizing effect by limiting bonding between snow grains. These graphs show visually what we've been talking about. The graph in the upper left shows avalanche potential as a function of temperature. As you can see, avalanche potential is lowest at air temperatures just below freezing and increases as temperature is reduced. The upper right graph shows the difference over time of avalanche potential in warm and cold conditions. Warmer air conditions stabilize the snowpack and reduce the likelihood of an avalanche. This is the condition we experience most commonly on Mount Hood. The lower graphs show the effect of upside down and right side up storms. The graph on the lower left is an upside down storm. As you can see, the avalanche potential increases as the temperature warms and wetter, heavier snow is deposited, increasing the loading on the dry, loose snow. The lower right graph shows a right side up storm, and as you can see, the avalanche potential does not increase significantly as the temperature is reduced and colder, lighter snow is deposited. There are environmental effects that could amplify temperature effects. One of these is solar radiation. Solar radiation has a big effect on snow surface temperature. Solar radiation or heating effects from the sun is highly variable. Depends on latitude, season, aspect ratio, aspect of the mountain, cloud cover, slope angle, and elevation. Solar radiation may not be a factor in winter months with shorter days and more frequent cloud cover. Solar radiation affects snow stability by weakening the bonds between grains of snow in the snow surface layer. When the bonds are weakened, the snow surface can become rapidly unstable. In addition, rapid melt can increase loading and percolate into buried weak layers, triggering slab avalanches. Solar radiation can also contribute to snowpack stability. Solar radiation heats up the surface layer, melting bonds. At night, the snow crystals refreeze, creating very stable melt-freeze crusts. This effect is most pronounced in the spring. Solar radiation combined with temperature cycling can create special dangers. For example, after a long cold spell, solar radiation creates rewarming and surface instability, which could trigger deep buried layers. The combination of rapid loading, rapid temperature change, plus a weak layer is especially dangerous. In the event days and nights are warm enough refreezing does not occur, solar radiation can trigger a wet slush avalanche or even trigger a slab avalanche by weakening a deep buried layer. In the event of prolonged periods of clear, cold nights, solar radiation can create temperature gradients that weaken the snowpack. More on this in Avy 2. Sky cover enhances the effect of solar radiation by trapping reflected long wavelength radiation, which increases air temperature. The corollary is also true. Clear sky results in very cold temperatures. In this case, the snow surface can be colder than the air temperature due to radiative cooling. This is the ideal condition for surface Hoar formation. The environmental factor that affects avalanche conditions is relative humidity. High relative humidity contributes to rime ice formation and creates more dense and cohesive slabs. High humidity combined with cold temperatures also contributes to enhanced surface Hoar formation. High humidity tends to be associated with warm, moist storms. Lower relative humidity reduces wind transport and may reduce the effect of heating cycles to reduce the likelihood of white slide avalanches. Surface Hoar is frozen dew. It forms most readily in cold, clear windless nights. On cold, clear nights, radiation losses reduce the snow surface temperature below the air temperature. Condensation of water vapor at the snow surface forms crystals on the snow surface. Surface Hoar can become buried depth Hoar, a weak layer, when buried under a subsequent snowfall. These can be long-lasting weak layers in cold snowpacks. Here are some examples of surface Hoar. You can see the crystals are highly faceted and have a feathery appearance on the surface. Particularly the picture on the right there shows surface Hoar very, very nicely. So we've discussed the effects of weather on snowpack stability. In order to use this information to assess avalanche risk, you need to have access to accurate weather information, precipitation, temperature, wind, etc. Moreover, you not only need to know the projections looking forward, but also the history. So where do you get this information? Luckily, we have some good resources to use here on Mount Hood. The primary website we use is NWAC, and the URL is given right there in the slide. This site gives weather, temperature, wind, and precipitation at multiple locations on Mount Hood across all resorts. The NOAA website, www.weather.gov, also gives site-specific weather info, including specific weather history. Other websites are listed on the slide. I encourage you to check them out. Which brings us back to our old friend, the Avy Triangle. Terrain: is the slope steep enough to slide? Snowpack: is there a consolidated layer over a weak layer? Weather: has the weather been changing rapidly, as in a lot of new snow over a short period to increase stability? And what will the trigger be to start the slide? This is the end of our discussion of the weather and its effect on avalanche potential.